All right, so we can officially start the third day of our workshop. And Krzysztof, I will make you the host, and you can start sharing your slides. Mhm.
Okay. Hello, everyone. I hope you're doing good and that notebooks are going smoothly. I'll try to now see the participants. Let others join. And at the beginning, I want to make a little bit disclaimer in yesterday's lecture. So I was trying uh, to derive the eigenvectors and eigenvalues of the Hadamard operator, of the not operator, I'm sorry. And I was stuck in this part here. But actually, the when you substitute the eigenvalue to this matrix like here and calculate and make an operation on a vector, some vector, you should get the vector 0, 0, which is also denoted here. So when we do that and calculate the resulting equations, minus a plus b equals 0, we actually get that a must be equal to b. And by the condition of normalization, this must equate to 1 over square root of 2 and 1 over square root of 2, which we confirm later. This is as the review and a quick note about yesterday's lecture. And today's lecture will be kind of a revision of yesterday's. We will cover more deeply the quantum states, especially operations on a unit circle, and which may involve rotations and also reflections. And we will cover how the reflections of a unit circle correspond to different quantum gates, such as Z gate, H gate, or X gate. And then we will talk about quantum tomography, what it means, and how to get our quantums, how to represent the quantum states from the measurements. So let me start by drawing the unit circle as we did it yesterday. So here we have our plane and the circle. And as you may remember, the states corresponding to 1, 0 were labeled as 0, and the state 1, 0, 0, 1 was represented as the 1 state. So now let's try to think what will happen if we apply a rotation gate, a rotation. So what if we apply a matrix so that this whole plane is rotated around this axis? Let's call this, for simplicity, we'll call this X, Z, and Y, and you'll see later why I call them, maybe not, maybe just stay with the traditional labeling. We will rotate our plane about this axis, about pi over 4 degrees. And what will happen is that this vector here gets transformed to here with angle pi over 4. And this vector here will be transformed to vector here, which is also pi over 4. Now, if you remember from yesterday or from a introduction of basic trigonometry, you should know that this is cosine. This value of this vector is cosine of pi over 4. And this value should be the sine of pi over 4. Likewise, this vector here gets transformed to minus cosine. I'm sorry, this gets transformed to, if this is pi over 4, then here we will have cosine of pi over 4. And here we will have value of minus sine of pi over 4. I'm covering this because this rotation gate will appear in the notebooks. So I believe that this may be quite relevant to bring you more of a theoretical background of how to deal with those rotation gates. So now our state of this vector becomes minus sine of pi over 4 and cosine of pi over 4. I see there's a question in chat, so I'll try to read it. And there's a reply to the question about the Hamiltonian. What's of the purpose of rotation? What are you getting? What is the purpose of rotation? So rotation is also a type of a quantum logic gate, and it will be the specific type of rotation will be a Y gate, which a Y gate, yes, which we have not covered yet, but I will talk about it in a second. So let's now try to represent this operation rotation of pi over 4 as a matrix. So we said that in order to construct a matrix, in the first column, we write where does the first vector, the 0 vector, land. And in the second column, after the transformation, and in the second column, we specify where does the 1 vector land. You may recall it from the first section, the first day. So in this case, we can see that I will try to make it a little bit bigger in a second. The first vector, 0 vector, after the transformation, lands in cosine of pi over 4 and sine of pi over 4. And the second vector lands in minus sine of pi over 4 and cosine of pi over 4. So this is where the first vector gets transformed to. This is exactly this. And this is where the second vector lands after the transformation. So this will be right here. And this particular example comes to be 1 over square root of 2, 1 over square root of 2. And now here's the minus 1 over square root of 2 and 1 over square root of 2. Okay, so in general, we also have a Y rotation gate, but unfortunately the Y rotation gate involves also the complex numbers. So unfortunately, because it's the it's not the scope of our lectures, because the complex numbers are, as also the name suggests, quite difficult to cope with. but you can think of the rotations to as a rotation about this axis that is perpendicular to our plane. And rotations are important because they also teach us how to deal with matrices and how to construct any state, any quantum state from the basic 0 and 1 states. I hope I answered your question about the purpose of those rotations, and I will see if there are any more questions about the chat, and I will admit also the people who are coming. How do you implement or program a Hamiltonian operator? This is a discussion I will cover after the lecture. So yes, but in general, we can apply a rotation about some different angle using the matrix cosine of theta, sine of theta. Next, we will have minus sine of theta and cosine of theta, where the theta can land in the of 0 and 2 pi. So let's try to calculate what happens when we apply this rotation about y-axis a few times. So doing it by hand, it will be quite tedious, but let's see. Actually, we can simplify the writing and say 1 over square root of 2 here, and it will be 1, 1 minus 1, 1. And let's see what we will get after on the state 1, 0. So on the state, we will get multiplying this with that, which is 1 plus 0. I'm sorry, 1 plus 0, which is from this here. And also 1 also plus 0, which is equal to, and also 1 over square root of 2 here in front of, which is equal to 1 over square root of 2, 1, 1. And let's now apply this operator once again on our resulting state to get a little bit more intuition how, in practice, how the matrices work. And here we have also 1 over square root of 2 from the vector itself. So now we have 1 minus 1 and 1 plus 1 from this multiplication here. And 1 over 2. Actually, no. Yes. That should be correct. 1 over... actually, this gives us 2. What do you mean you use rotation to build states, and why do you need the states created by rotation? Well, those come up in some quantum algorithms. To be able to create any state, you sometimes in different algorithms, we will build them later. We need to create some states in order to be able to follow the algorithm itself then. Or maybe the quantum states you're trying to prepare represent some physical observations you did, or something else. So now we have 1 over 2 from the multiplication of here, and now we have 1 over 2, 0, 2. And this gives us back the vector 0, 1, which is 1. So you can see manually that applying those matrices, we get the different states of the qubits. Okay, so let me now move on to reflections, and especially we'll cover Z, H, and X gates in the sense of rotation. So let's begin with the quantum operator Z. And as you can recall from yesterday's lecture, the Z operator looks like this. And as you may also recall, the one state gets transformed to I'm sorry, the zero state is transformed to zero state, and the one state is transformed to -1 state after applying this Z operator. So let's take a qubit, for example, this one, and we will instate some state psi, and we will say that this state is, for example, cosine of theta. We'll take some arbitrary state theta. Cosine of theta of 0 vector plus sine of theta of the 1 vector. And this we will call as we mentioned before, a superposition of those states. And you can also confirm that this is a valid state because this squared, so cosine squared of theta plus sine squared of theta is equal to 1. And this is how we defined our proper quantum state before. So now applying the Z operator to our state psi, we will get cosine of theta of 0 and minus sine of theta of the 1 operator. And this minus comes from here, from the way the Z operator behaves. So now let's try to rewrite our quantum state with this minus sign. So now we know that this is cosine of theta, so this value stays. We can also rewrite this as cosine of theta minus sine of theta. Again, here with minus. So now you see that the value of the cosine stays the same, of the x value stays the same, right? So it's here, but in the y component we have a minus sign. So our transform vector will be the arrow here, and we also have theta. And therefore, by this example, can you come up with a way to say what is the reflection about what axis? Can you say that? Here's a reflection or rotation. What do you think? You can write it in the chat, or you can unmute yourself and say it. And I really would like to see your participation here. What do you think is the rotation or reflection about what axis? Why? Sorry, x-axis. Yes, this is reflection about x-axis. X-axis, exactly. So this is our plane of, I'm sorry. This is our plane of reflection. Right. So you can also think of the z gate as a reflection about the x-axis in case of the real valued qubit. Now let's talk about the Hadamard gate. And this gate is more complicated a little bit. And we know from yesterday that applying 0, a Hadamard gate on the vector 0, gives us 1 over square root of 2, 0, plus 1 over square root of 2, 1. And we will call this state a plus state because it's much easier to write a plus state instead of the whole equation here. And this is also equal to 1 over square root of 2 over 1 over square root of 2. We also know from yesterday that applying Hadamard gate on 1 gives us 0. But here we have minus 1 over square root of 2, 1, which is equal to minus. We just called it arbitrary state to be able to represent it more easily. 1 over square root of 2, and here also here goes the 1 over square root of 2. So based on this information, maybe you'll be able to say what does the Hadamard gate do? So we will draw our I don't remember okay. So here's our 0 state. And it gets transformed to something like this. Right? 1 over square root of 2 over 1 square root of 1 over square root of 2 and 1 over square root of 2. So this is our 0 state. This is our plus state. But now the 1 vector, after the transformation, so after applying the gate, I'm sorry, I forgot the minus here, gets transformed to 1 over square root of 2, and here goes the minus, so gets transformed to something like this. Here's the minus. So based on this information, can you say, is it the operation? Is it the reflection? And if it is a reflection, then what should be, maybe first tell me, is it a reflection or a rotation? X, how did we get 2 times both? Actually not. It's not both. How do you get 2 times psi when z is reflecting on x? What do you mean 2 times psi? Rotation? No, it's not also not a rotation. It's a reflection, but reflection then. Yes, this is reflection, and I can prove it to you graphically by trying to draw a, maybe I can add a different pen, different color, or red. Plum is perfect. Okay. So I'll try to decrease. Okay. So actually the reflection is here. This is the line of the reflection, and the angle theta should be pi over 8. Okay, so now maybe it's not the perfect drawing, but in the notebooks you will be able to see that this is actually a reflection about the x-axis, and you will be able also to draw other states, random states, for example, something like this, and be able to confirm that after this reflection, you'll land something like something like here. Yes. Okay. So now we have covered 2 of our gates, and we're left with the X gate. So in case of the X gate, the 0 after applying the X gate is transformed to 1. And the 1 state is transformed to 0. So let's draw this once again on the unit circle and see what we can get. So we have 0. And this gets transformed to 1. And we have also 1 that gets transformed to 0. But we can also, maybe it's not very obvious now whether it's a reflection or rotation. So maybe we can try adding more states. And for example, let's try to get the state, the plus state. Let's try to see how this reacts. Which is 1, 1. So the X gate was 0, 1, 1, 0. And applying it to the plus state, which is square root of 2, 1, 1, will give us square root of 1 over square root of 2. And let's see now what do we get. Multiplying 0 by 1 gives us 0 plus 1. I'm sorry, plus 1 plus 0 plus 1, I'm sorry. 0 plus 1. And multiplying here, we have 1 times 1, which is 1, and 0 times 1, which is 0, which is 1 over square root of 2 over 1 over square root of 2. And you can see that this state is exactly the same state after the transformation. So we can see once again that the plus state, X gate applied on the plus state is also the plus state with an eigenvalue of 1. So this is an eigenvector of the x operator. So now let's try to compute X state on the minus state, because now it will be very clear what does this gate do. And we also get useful to more multiplication. Sorry, now we have, in case of the minus state, we have 1 and minus 1. And now after the multiplication, we get 0 times 1, which is 0, 1 times minus 1, which is minus 1, 1 times 1, which is 1, and 0 minus 1, which is 1. Now you can see that the minus jumped from here to here. And we can write the state. So therefore, it is minus 1 over square root of 2 and 1 over square root of 2. A lot of writing, a lot of math, but I believe it is very important to once in a lifetime do it to understand those concepts. So can you tell me now, what does this gate do? Is it a rotation or reflection? Do you have any ideas? Reflection, yes. Reflection around a line. And it's a line that happens to be, this angle happens to be pi over 4. Someone wrote in the comment, yes. Can you explain how this geometry math applied to a real qubit? Well, in normal circumstances and in well, creating an algorithm, you don't need to draw the state of the qubit each time, because this aims to give you the intuition about quantum computing and quantum states, how you can visualize them, and to give you the analogy and an intuition to think in terms of linear algebra and quantum computing. So if you apply an operator, what does this operator do to a certain qubit in real life? But for example, in real life, what you could imagine in case of what I like to think of is the, once again, Stern-Gerlach experiment with the magnetic field. So in that case, the you can think of this experiment as a quantum gate, but if you did not make the measurement, let's say. So if you think about a physical problem with the external magnetic field, the spin can be either aligned or anti-aligned. And as we said earlier, the qubits can go either to the upper branch and to the lower branch. And this experiment can be represented in terms of the mathematics as the Z-gate. So we have two possible outcomes of the experiment, right? So in one circumstance, the energy is the y eigenvector is, as we said, is 0, 1, which is 1 times 0, 1. So you can say that the energy of this system is 1, but you can also imagine a qubit in the state of 1 and 0. And in that case, the energy of this system, I'm sorry, I made a mistake here. It's actually reverse. It's quite easy to get. So when the spin is anti-aligned with the magnetic field, the energy is negative, but if it is aligned, the energy is positive. And it's like the intuition you may think of applying quantum gates, either by a magnetic field or a laser. And in normal quantum computers, you have trapped ions or a superconducting circuit, and you also manipulate the state of both atom and a circuit by applying an external electromagnetic field. This was a quite elaborate side topic, but I hope it explained the question of of how to explain geometry math in the real case scenario and the real qubit. Is a qubit a circle? A qubit is not a circle. A qubit is the state of some system, but it's very convenient to think of it as a state on the circle. Okay, so let me go back with our example, and we said that this is a reflection about the pi over 4 axis. And in general, we can write a reflection of our. Let's try now to formulate a matrix in the same case. Sorry. Let's try to form a general matrix about the reflection. But here we had the case of the rotation. But now let's try to formulate the very similar matrix in case of the reflection. So we want to have a reflection about any given angle. So let's say we have some angle theta, and we want to find what is the resultant matrix of such a system. So if you have a reflection about this line, then the qubit 0 will be transformed to a state with also the angle theta here. So the resultant state will be the resultant state here will be cosine of 2 theta and sine of 2 theta. I hope you can see that this value here is the cosine of 2 theta, and this value here is the sine of 2 theta. But what happens with our 1? Our 1 now, instead of going through the same angle, we have now some different angle, and this angle will be pi over 4 minus theta. I'm sorry, not pi over 4, but pi over 2 minus theta. Now this vector here gets transformed to something like, it's really hard to view it right here. Something like here, which will be this state here will be actually pi over 2 minus 2 theta. Right? No, not exactly. This should be, I really need to think about this. This should be, but we know the value here. I'm sorry. This angle is, so this angle is 2 minus 2 theta. No, that's, it's really quite complicated. This value should be the same. Or is it? I got confused a little bit, I'm sorry. But actually, this value right here should be sine of 2 theta. And this value should be the minus cosine of 2 theta. And this is quite similar when in the case of the reflection. You can see here, but instead of the theta, in case of the rotation, we had just theta. But in case of the rotation, we have 2 theta instead. So let's try to draw this a little bit cleaner. So instead of this, I'll try to write just the state of this this cubit, which is sine of 2 theta and minus cosine of 2 theta. This is how the reflection works. So now the matrix of reflection about the line of angle theta will be where the x vector lands, when the 0 vector lands, and where the y vector lands. So the 0 vector after the transformation lands in position cosine of 2 theta and sine of 2 theta. Likewise, the second vector, the y, the 1 vector, after the transformation lands in a position, so this is here, lands in a position sine of 2 theta and minus cosine of 2 theta. And this is so this is also where the x lands is 0 vector lands and where the 1 vector lands. Yeah, so this is a general formulation of the reflection about a line in certain angle. I see a quantum operator is an electromagnetic wave. I mean, a quantum operator can be, in real case, can be, this is a replying to a question. I'm right now replying to a question. A quantum operator can be implemented as a electromagnetic wave. There are some other implementation of quantum gates, especially it's quite very tricky in case of the photonic quantum computers. But in case of the superconducting trapped ion computing, quantum computing, the quantum gates can be implemented as a electromagnetic wave of certain pulse and duration. Both angles on the sides of the reflection axis are the same. Yes, thank you for the comment. Okay. So, so now a little bit word about quantum tomography, what it is, and how to formulate it. So quantum tomography aims to answer the question, what is the state of our qubit based on the measurements? So let's say we prepare 1000 qubits in the same state. So you can imagine the state of the qubit as an arrow on the circle. So we prepare all the qubits in the same state, so one arrow, and then we perform measurement. But you can measure only the distribution of 0 and 1. So, for example, let's begin with by saying that after a series of measurements, this is a bar graph, as you could see on the in the Qiskit. There's a bar graph that counts how many zeros we measured and how many ones we measured. Qubits in state 0 and qubit in state 1. So let's say we measured 500 qubit in state 0 and also 500 qubits in state 1. So do you have any ideas what the state of the qubit we measured was? Can you say maybe write in the chat the angle I should write to the qubit? So what should be the superposition? Yes, exactly. The superposition, you're right, of 2 qubits. But what should be the resulting arrow? Where I should draw the arrow? If I draw here, it's not a really good representation because in this case, you would measure more qubits in state 0 and less qubits in state 1, right? So where this arrow should land. Superposition, yes, also correct. This is a superposition of both states. Pi over 4. Thank you, Marek, for the comment. You're right. But it's not the only answer. Can you think of another answer? So as we said before, this pi over 4 is the plus state, which is the 1 over square root of 2. 1 over square root of 2. But the probability of measuring 1 is this value squared. So 1 over square root of 2 squared, which is equal to 1 over 2. And this matches our statistics and the distribution, but also this value of the probability of measuring one state is also 1 over square root of 2 squared, which is 1 over 2, and is also match our probability distribution. Yes, I can now see your comments, more of your comments. there are 3 pi over 4, 5 pi over 4, and 7 pi over 4. That's exactly true. So we can also have different states which are here, which will give us exactly the same distribution, because this state is square 1 over square root of 2 minus 1, 1. This state is the minus state, which is 1 over square root of 2 1 minus 1. And the last state is 1 over square root of 2 minus 1 minus 1. So by the measurement of a qubit, you are not able to recover its state because of the phase. During the measurement, we lose the phase of the qubit. So you can also think of the phase as those minuses here or here or here and here. So we don't know whether the qubit, in which quadrant the qubit was after the measurement. We lose this information. But nevertheless, this information is very important in case of the quantum algorithms. So actually, different qubits in different phases interact with each other via quantum gates in different ways. But we are not able to measure the phase of the qubit, but it becomes important in the case of algorithms. So now I would like to talk to you about the concept of a global phase. What is the global phase, and how is it different from reality? So in a case of our Z gate, we had a something. I mean, we had the operator which, after applying to 1, gave us the state -1, right? I also wrote it somewhere here. Sorry, somewhere here, yes. And you can also see the reflection here. So the state 1 after applying the Z gate gains transformed to -1. But in fact, if you want to now try to measure this state, you would also get the probability of -1 squared, -1 squared, which is equal to 1. So after applying the Z gate on the qubit, you are not able to tell a difference between those two quantum states. And this is called a phase, or a phase problem you may also think, you may also call. But what now with the qubit 0 and -0? We are also not able to distinguish between those two states. And actually, the both states, the 0 -1 and 0 -0, are mathematically different, but physically you're not able to distinguish between those two states because you lose the information about the phase in the measurement. So that's why this you may also you may also hear the term a global phase. So a global phase is something which is maybe mathematically relevant, but you don't have the access to the global phase in the real world. Okay, is there an analog to wave function collapse when the state is measured in quantum computing? Yes, because I mean, a wave function in terms of a particle moving, you can imagine a wave function of a particle that's moving in, oh, I'm sorry, that's moving in space. Let's consider a one-dimensional qubit. And the probability of measuring a particle moving in the x direction is given by the amplitude of the wave function squared. So it's something like this, this, and this. So you have very great probability of finding a particle. Here I come with some arbitrary wave function. And in case of the measurement, when you try to now, for example, shoot a photon on this particle and locate it in space, then you can try to you would see, for example, that this particle was in position 0.5. And this wave function, after the measurement, becomes a Dirac delta function. And it's quite a very special function because it is it's a delta Dirac function, x of minus x prime. It happens that the area under this curve is equal to 1, but the width of this peak should, so the, let's say, delta x, this delta x should approach 0. It's very special and very mathematically useful function. But after a measurement, you can say in which position you found your particle, and you have also to remember about, you have to remember about the Pauli principle. The Heisenberg uncertainty principle. And I believe it's something like, I will check to check this. Heisenberg is greater than some constant, which is h squared over 2. This is in the case of a wave function, continuous wave function. But now our wave function is a discrete wave function. So now let's say we have some state A0 plus B1. And now after the measurement, you can also say the wave function collapses. Although some physicists don't really like this nomenclature that the wave function collapses, because they cannot say what this actually means. But yeah, you could say that after the measurement, you can only get one state of the qubit. So after the measurement, the wave function collapses to, for example, 0. The wave function collapses is measured in quantum computing. Yeah, so this is exactly, maybe not analogy, this is in fact what happens. So after the measurement, your qubit is in fact in state 0 because you have already measured it. So likewise in the example of the Stern-Gerlach experiment, you don't know whether your atom had the spin aligned or anti-aligned with the magnetic field, but after they pass through the experiment, you can now with certainty say that the atom had spin aligned or anti-aligned with magnetic field. So actually the act of measurement change the state of the quantum system. Okay, thank you for your answer. Yes, and I think that it is it for tomorrow, for today from my side. Have a great fun solving the notebooks. Do you have any questions left? I cannot see any. Today's lecture will be quite difficult, so please make sure to review all the all the topics we have covered so far, because tomorrow we will start with quantum teleportation and phase kickback algorithms, and now we will cover more of a quantum algorithms and the quantum weirdness and quantum phenomena topics. Okay. So if there are no questions, then thank you for today and see you tomorrow. Yeah, goodbye.